In this video, we are going to talk about some more exceptions to the Lewis model. Now, I'd just like to say a word about that. Just because there are some exceptions doesn't mean that the model isn't helpful. It is useful in a lot of situations, but there are some times when it may not be the best way to think about our molecules. However, this can be a really useful way for understanding how atoms bond to each other, and so it's still a useful model to try to work with, even if there are some exceptions. So one of the first limitations we've talked about is electronegativity. So remember that electronegativity is the ability of an atom to attract electrons to itself in a bond. And the Lewis model does not show this unequal sharing of electrons. This here is called an electrostatic potential map. It lays over our molecule of HF, which is hydrofluoric acid. On this end, where it's like a reddish orange, this is negative. This indicates that the electrons spend more time on the fluorine side than they do the hydrogen side. This end is in the blue range. These are the positive charges. Now, these aren't full charges. This isn't an H plus and an F minus. We use this delta to indicate that is a partial positive and a partial negative. This hydrogen is still sharing electrons with this fluorine, but it's not sharing them evenly. Another way to indicate that this is a polar covalent bond is to use a dipole moment. When using a dipole arrow, you point the head toward the electronegative end, or toward the partially negative end. This is a vector, so it has momentum and direction. It is possible for vectors to cancel out. So if there was one vector pointing in this direction and another pointing in the opposite direction, overall, the molecule would not be polar, even if it was made up of polar bonds. In this case, we only have one polar bond. There's nothing to cancel, and so we have a polar bond and a polar molecule. Another limitation or exception is having odd electron species, or, as you might have heard of them before, free radicals. Nitrogen monoxide is an example of a free radical. Why don't you try to draw the Lewis structure of nitrogen oxide? What you'll notice is that nitrogen comes with 5 valence electrons and oxygen comes with 6. If you add both of those together, you get 11, which means that there will be one unpaired electron. Here's our Lewis structure of nitrogen monoxide. In this one, we have a single bond between the nitrogen and the oxygen. And then we have 8 pairs and 1 single electron. So 9, 10, 11. Here, we have 6 pairs, 2 bonding pairs, and a single electron. These are highly reactive species. You may have heard of antioxidants. These help prevent free radicals from damaging your tissue. These work by inhibiting the oxidation of other molecules. A healthy atom has all of its electrons, or shall we say a stable atom. Free radicals are not very stable. They have a very high electron affinity, so they attract electrons readily. Antioxidants have a very low ionization energy. They are able to give up an electron. The free radical accepts the electron from the antioxidant, and the other atoms are left alone at limiting the damage. So this happens in your cells all the time. The compounds that make up your cells can be damaged by free radical species in your body or in the environment. This was going to be oxidized. In other words, it was going to lose electrons. This antioxidant gives up one electron because it has a low enough ionization energy that it is able to do so. This prevents the free radical from taking an electron from this other atom. Vitamin C and vitamin E are really common free radical inhibitors. So they are these antioxidants that are very common in beauty products, in our diet, and they are helpful to stabilize free radicals in our body and make them into more stable compounds. They have a lot of electrons they can easily donate. These molecules do. And when one of these molecules donates an electron, this molecule becomes more stable. The antioxidants are not as reactive, and so there's no real damage that's happening to your tissue. Vitamin C is especially important in the beauty industry. It is very commonly found in face lotions and skincare products, and that is to help reduce the oxidizing effect of the sun on your skin. Another limitation and exception to the Lewis model are these incomplete octets. So we have a couple of examples here. Let's look at boron first. So you'll notice here that boron only has 3 lone pairs, which means it has a total of 6 electrons, and it doesn't have an octet. Fluorine, these have their octets satisfied because there's 2 here, 4, 6, 8. So each fluorine has this. You'll notice with aluminum, it's the same thing. These two elements, boron and aluminum, are in the same group on the periodic table. So one would expect boron and aluminum to react similarly because they have a similar number of valence electrons. We call these incomplete octets because they are considered full with 6 electrons instead of 8. Now, how do we know that it's really like this and there's not some other way of writing the structure in order to give us a complete octet? Let's use boron as an example again to see if boron always has an incomplete octet. In this example, we have used arrows to push electrons around to make resonance structures. So this pair of electrons comes down here and makes a double bond. Now, boron has a complete octet. All of the fluorines also have a complete octet. 2, 4, 6, 8, 2, 4, 6, 8. So maybe this formation is better to give everything a complete octet. But we can't forget about formal charge. Remember, this is our bookkeeping method to check to see what the total electrons are that you can kind of think of this as the atom having access to. So remember that formal charge is not real. It is not an actual charge on a molecule or an atom within a molecule. But what it is a way to keep track of electrons and where they, to make sure that you have enough electrons and that they are distributed appropriately. So to calculate the formal charge, we take the number of valence electrons and we subtract the sum of the non-bonding electrons and half the bonding electrons. Let's do this for boron trifluoride. In this first example, boron has 3, and it has a 0 non-bonding electrons, and it has 4 bonding electrons, it has 8 bonding electrons, half of which is 4. So 3 minus 4 is -1. Now if we look at the fluorine, we've got 7 valence electrons for fluorine and 4 non-bonding electrons, because that's these guys right here. And then there are 2 bonds, so there's a total of 4 bonding electrons. Half of that is 2. So 7 minus 6 is +1. And then for these other fluorines, they've all got 7. And you subtract 6 for the non-bonding electrons, and then subtract another 1 for half of the bonding electrons. So we get a formal charge of 0. So let's put these formal charges in. So all 3 of these resonance structures show us that boron has a -1 formal charge and fluorine has a +1 formal charge. What formal charge rule do these resonance structures violate? If you think back to our last exercises and videos, the general rule for formal charge is that the negative charge needs to be on the most electronegative atom. If you look at the trend for electronegativity, fluorine is the most electronegative atom. This means that we are violating that rule of putting the negative charge on the most electronegative atom because boron is negative and fluorine is positive. So this means that this is likely not a large contributor to the structures that exist for boron trifluoride. And this is much more common. Now, do these molecules spend any time in this orientation? We actually have experimental evidence that suggests they do. Double bonds are shorter and stronger than single bonds. We have instruments and experiments that can determine the strength and the length of a bond. While no single bond is quite as strong or short as a double bond, none of these bonds themselves are the same strength and length of a single bond. This means that we can say that boron trifluoride has a small amount of double bond character, which means that this is the predominant resonance structure, but that these resonance structures do play a little bit of a role in determining the overall structure of boron trifluoride. Our last limitation and exception to the Lewis model is the expanded octets. These only happen in the 3rd row and beyond. So, for example, arsenic and sulfur, these can expand and have more bonds than you would expect based on the octet rule. Sulfur has 12 bonding electrons and arsenic has 10. Let's take a look at an example where we can observe this expanded octet. Let's look at sulfuric acid. In this structure, we have charges on 2 atoms here. Everything is in single bonds. And on this structure, we have a double bond here. And this gives sulfur 5 bonds. We have fewer formal charges, and we have the negative charge on the more electronegative atom. So this structure is slightly more stable. Experimentally, we do see that there is some double bond character of this. It's not quite full double bond, but it's pretty close to having a double bond. So this is experimental evidence that sulfur can handle an expanded octet. Why? Well, the answer is just plain old size. The bigger an electron is, the more space their electron orbitals have, and they can have that expanded octet because you start to get into those d orbitals instead of just having the s and the p orbitals that hold 8 electrons.